Picture this. It's 1,970. A 58-ton monster of steel and ambition sits abandoned in a German testing facility. Its revolutionary rotating driver capsule hangs motionless like a broken carnival ride. The most expensive tank ever conceived has just been declared dead on arrival. The cost? Nearly $2 billion in today's money. The result? 0 operational tanks. Welcome to Never Built, where we explore the most spectacular technological failures in history. I'm your host, and today we're diving deep into the MBT-70, a tank so advanced, so complex, and so catastrophically over-engineered that it collapsed under the weight of its own ambition. If you're fascinated by the stories of technologies that never made it, hit that subscribe button and let me know in the comments what other failed projects you'd like us to investigate. The MBT-70, or Main Battle Tank 70, wasn't just another military vehicle. It was supposed to be the ultimate weapon, a tank that could survive nuclear warfare, outrun anything on the battlefield, and deliver devastating firepower with pinpoint accuracy. Instead, it became the most expensive lesson in engineering hubris ever recorded. But how did the world's two most advanced military powers, the United States and West Germany, create such a magnificent disaster? The answer lies in the paranoia and technological optimism of the Cold War era, when the impossible seemed merely difficult, and money was no object in the race to build tomorrow's weapons today. The story begins in the early 1960s, when American and German engineers sat down to design what they called the tank of the future. What they created instead was a mechanical nightmare that would drive test crews to nausea, bankrupt entire defense budgets, and ultimately teach the world that sometimes the most advanced technology is also the most fragile. The MBT-70 featured innovations that seemed like science fiction. A hydropneumatic suspension system that could make the tank crouch like a predator or lean into turns like a motorcycle. A 152mm gun launcher that could fire both conventional shells and guided missiles. And most bizarrely, a rotating crew compartment that kept the driver facing forward no matter which direction the turret pointed. That last feature, the rotating driver's station, would become the tank's most infamous characteristic. Imagine being strapped into a chair inside a washing machine while someone spins the drum. Now imagine trying to drive a 58-ton vehicle while experiencing that sensation. Test drivers reported severe motion sickness, disorientation, and in some cases, complete inability to operate the tank effectively. The irony was palpable. In trying to create the perfect tank, engineers had built a machine that its own crew couldn't tolerate. The MBT-70 was like a sports car that made its driver too sick to drive, or a computer so advanced that nobody could figure out how to turn it on. But the rotating capsule was just the beginning of the MBT-70's problems. The tank's complexity was staggering. It required specialized maintenance equipment that didn't exist, replacement parts that cost more than entire conventional tanks, and training programs so extensive that crews needed months just to learn basic operations. What do you think? Was this pure ambition or a dance with destiny? Let me know in the comments. The financial numbers tell their own story of disaster. Initially budgeted at $300 million for the entire program, costs spiraled to over $1.5 billion. And that was in 1970s money. Adjusted for inflation, the MBT-70 program cost nearly $10 billion in today's currency, making it one of the most expensive military failures in history. Each prototype tank cost approximately $25 million, more than an entire squadron of fighter jets. For comparison, the Soviet T-62 tank, which the MBT-70 was designed to counter, cost roughly $100,000 per unit. The Americans and Germans were spending 250 times more money to build a tank that couldn't even complete basic field trials. The collapse came suddenly and decisively. In 1970, after nearly a decade of development and billions of dollars spent, the U.S. Congress pulled the plug. The official reason was cost overruns, but insiders knew the truth. The MBT-70 had become technologically unfeasible. It was too complex to build, too expensive to maintain, and too unreliable to deploy. The German government followed suit shortly after, canceling their portion of the program and leaving behind a handful of incomplete prototypes and a mountain of engineering documentation that would later prove more valuable than the tanks themselves. But here's the fascinating twist in this tale of failure. The MBT-70's death gave birth to one of the most successful tanks in military history. The lessons learned from the MBT-70's spectacular collapse directly influenced the development of the M1 Abrams tank, which would go on to dominate battlefields for the next 4 decades. The Abrams took the MBT-70's best ideas, advanced armor, powerful engines, sophisticated fire control systems, and stripped away the over-engineering that had doomed its predecessor. Where the MBT-70 had a rotating driver's compartment, the Abrams had a simple, fixed position. Where the MBT-70 had a complex gun launcher system, the Abrams had a reliable conventional cannon. In essence, the MBT-70 served as an expensive prototype for what would become America's premier battle tank. Its failure taught engineers the crucial difference between innovation and overcomplication, between advanced technology and practical application. To understand how the MBT-70 became such a spectacular failure, we need to travel back to 1963, when the world stood on the knife's edge of nuclear annihilation. The Cuban Missile Crisis was fresh in everyone's memory. The Berlin Wall cast its shadow across Europe, and military planners on both sides of the Iron Curtain were convinced that World War III was not a matter of if, but when. In this atmosphere of barely controlled paranoia, American and West German defense officials met in a series of classified conferences to discuss a terrifying reality. Soviet tank technology was advancing rapidly, and NATO forces were falling behind. Intelligence reports suggested that the Soviets were developing new main battle tanks that could outgun and outmaneuver anything in the Western arsenal. The solution, they decided, was to leap ahead of Soviet development by creating a tank so advanced that it would render all existing armor obsolete. This wasn't just military planning. It was technological warfare, an attempt to win the Cold War through sheer engineering superiority. The partnership between the United States and West Germany made perfect sense on paper. America had the research capabilities, the advanced materials, and the massive defense budget. Germany had the world's most experienced tank designers, many of whom had worked on the legendary Panzer tanks of World War II, and a desperate need to defend against Soviet armor massed just across the border. The initial meetings were filled with optimism and grand visions. American generals spoke of tanks that could survive direct nuclear strikes and continue fighting. German engineers proposed revolutionary suspension systems and armor designs that would make tanks nearly indestructible. Together, they would build the ultimate weapon. The project was officially designated MBT-70, with MBT standing for Main Battle Tank and 70 representing the target year for deployment. The timeline was ambitious but not impossible: 7 years to design, test, and produce a revolutionary new weapon system. From the beginning, the MBT-70 was conceived as more than just a tank. It was to be a complete battlefield system, capable of engaging enemy armor, aircraft, and fortifications with equal effectiveness. The specifications read like science fiction: a top speed of 45 miles per hour, armor capable of withstanding direct hits from any existing anti-tank weapon, and a main gun that could fire both conventional shells and guided missiles. The nuclear warfare requirement drove many of the tank's most exotic features. The crew compartment was designed to be completely sealed and pressurized, with its own air filtration system capable of removing radioactive particles. The tank's electronics were hardened against electromagnetic pulse, and its engine was designed to operate on contaminated fuel if necessary. But it was the mobility requirements that led to the MBT-70's most innovative and ultimately problematic feature: the hydropneumatic suspension system. Traditional tank suspensions used steel springs and shock absorbers, which limited how low a tank could crouch or how much it could lean. The MBT-70 system used hydraulic rams and compressed air to actively adjust each wheel independently. This meant the tank could kneel to reduce its profile when firing, lean into turns to maintain stability at high speeds, and even adjust its stance to compensate for uneven terrain. In theory, it was brilliant. In practice, it required a computer system to manage the constant adjustments, and this was 1963, when computers filled entire rooms and had less processing power than a modern calculator. The firepower requirements were equally ambitious. The MBT-70 would mount a 152mm gun launcher system capable of firing the new Shalala guided missile. The Shalala was itself a revolutionary weapon, a missile that could be fired from a tank gun and guided to its target by laser designation. The combination of the massive gun launcher and the advanced fire control system meant the MBT-70 could theoretically engage and destroy enemy tanks at ranges exceeding 3 miles, far beyond the capability of any existing tank. It was like bringing a sniper rifle to a knife fight, except the sniper rifle weighed 58 tons and cost $25 million. The crew protection requirements led to perhaps the most controversial design decision in the entire project: the rotating crew compartment. Traditional tanks had the driver in the hull and the gunner and commander in the turret. When the turret rotated to engage targets, the driver would lose visual reference and have to rely on periscopes or radio commands. The MBT-70's designers decided to solve this problem by putting the entire crew in the turret, with the driver's position mounted on a rotating platform that would keep him facing forward regardless of turret position. It was an elegant solution to a real problem, but it created a much bigger problem in return. The psychological effects of the rotating compartment were not fully understood until testing began. Drivers reported severe motion sickness, disorientation, and in some cases, complete spatial confusion. Some test drivers had to be helped out of the tank after short driving sessions, and several refused to operate the vehicle after experiencing the rotating compartment. But in 1963, these problems were still theoretical. The project moved forward with tremendous momentum, backed by virtually unlimited funding and the highest levels of government support. Both American and German officials saw the MBT-70 as a potential war winner, a technological breakthrough that would give NATO forces decisive superiority over Soviet armor. The early design work proceeded smoothly, with teams of engineers on both sides of the Atlantic working around the clock to solve technical challenges. Advanced materials were developed, new manufacturing techniques were pioneered, and prototype components began taking shape in classified facilities. By 1965, the project had consumed over $100 million and employed thousands of engineers, technicians, and support staff. The first prototype was scheduled for completion in 1967, with full production beginning in 1970. What nobody anticipated was how the complexity of the MBT-70 would compound exponentially as development progressed. Each advanced system required its own support systems, which required their own backup systems, which required their own maintenance protocols. The tank was becoming less like a weapon and more like a mobile research laboratory. The Cold War context that had driven the project's creation was also beginning to change. By the mid-1960s, both superpowers were discovering that nuclear warfare was too terrible to contemplate, and conventional warfare was too expensive to sustain. The focus was shifting from massive tank battles to guerrilla warfare, counterinsurgency, and limited conflicts. But the MBT-70 program had developed its own momentum, driven by institutional inertia, political commitments, and the genuine belief that technological superiority could prevent war rather than simply win it. The tank had become more than a weapon. It was a symbol of Western technological prowess and a demonstration of NATO unity. By 1966, the MBT-70 had evolved into something that would have been unrecognizable to its original designers. What started as an ambitious but achievable tank had become a mechanical monster of staggering complexity. The engineering challenges were no longer just difficult, they were beginning to approach the impossible. The heart of the problem lay in the tank's revolutionary systems, each of which was pushing the boundaries of 1960s technology. The hydropneumatic suspension alone required over 200 individual components, including hydraulic pumps, pressure accumulators, electronic sensors, and a primitive computer system to coordinate everything. This computer system, called the Ride Control Unit, was itself a marvel of miniaturization for its time. Weighing over 300 pounds and requiring its own cooling system, it was responsible for making thousands of calculations per second to adjust the tank's suspension in real time. The problem was that computer technology in 1966 was still based on vacuum tubes and early transistors, making the system both unreliable and incredibly power-hungry. The tank's electrical system became a nightmare of complexity. Traditional tanks had relatively simple electrical needs: lights, radio, and basic engine controls. The MBT-70 required enough electrical power to run a small town, with systems for the suspension computer, the fire control computer, the environmental control system, the rotating crew compartment, and dozens of other electronic subsystems. The main engine, a Continental AVDS 1790 diesel producing 1,500 horsepower, was powerful enough to propel the 58-ton tank at speeds exceeding 40 miles per hour. But it also had to generate enough electricity to power all the electronic systems, which meant adding multiple generators, voltage regulators, and battery backup systems. The transmission system was equally complex. To handle the enormous power output and provide the precise control needed for the advanced suspension, engineers developed a hydrostatic transmission, essentially a hydraulic system that could infinitely vary the tank's speed and direction. It was smooth and responsive, but it was also incredibly complex and prone to failure. The fire control system represented another leap into uncharted territory. The MBT-70's main gun was stabilized in both elevation and traverse, meaning it could maintain accurate aim even while the tank was moving at high speed over rough terrain. This required gyroscopic sensors, hydraulic actuators, and a ballistic computer that could calculate firing solutions in real time. The ballistic computer was particularly problematic. It had to account for target range, target movement, wind speed, ammunition type, barrel wear, and dozens of other variables. In an era when most calculations were still done with slide rules, this computer represented a quantum leap in battlefield technology, assuming it worked. The Shalala missile system added another layer of complexity. The missiles themselves were marvels of miniaturization, packing sophisticated guidance systems into a package small enough to fit in a tank gun. But they required their own launch control system, guidance computers, and laser designators, all of which had to be integrated with the tank's other systems. The rotating crew compartment presented unique engineering challenges that had never been encountered before. The driver's position had to rotate smoothly and silently while maintaining electrical connections for controls, communications, and displays. This required slip rings, rotary joints, and a complex mechanical system that could handle the stresses of combat operations. The psychological effects of the rotating compartment were becoming increasingly apparent during testing. Drivers reported not just motion sickness, but complete disorientation and loss of spatial awareness. Some described feeling like they were floating in space or spinning in a washing machine. The rotation mechanism worked perfectly from an engineering standpoint, but the human factor had been completely overlooked. The armor system was another engineering marvel that created its own problems. The MBT-70 used advanced composite armor, layers of steel, ceramics, and other materials designed to defeat the most powerful anti-tank weapons. But this armor was not only heavy, it was also incredibly expensive and difficult to manufacture. Each armor panel had to be precisely manufactured and fitted, with tolerances measured in fractions of millimeters. The manufacturing process required specialized equipment, trained technicians, and quality control procedures that added months to the production timeline and millions to the cost. The environmental control system was designed to keep the crew alive and functional in a nuclear, biological, or chemical warfare environment. This meant a completely sealed crew compartment with its own air supply, filtration system, and atmospheric controls. The system could maintain positive pressure inside the tank, filter out radioactive particles, and even provide emergency oxygen for extended periods. But the environmental system also had to work with the rotating crew compartment, which meant flexible connections, rotating seals, and backup systems in case the primary seals failed. The engineering complexity was staggering, and the potential failure points were multiplying exponentially. What do you think drove engineers to create such complexity? Was it the pursuit of perfection, or simply Cold War paranoia? Share your thoughts in the comments. The maintenance requirements for the MBT-70 were becoming a serious concern by 1967. Traditional tanks could be maintained by crew members with basic tools and training. The MBT-70 required specialized diagnostic equipment, computer terminals, hydraulic test stands, and technicians with advanced training in electronics and computer systems. A simple oil change on a conventional tank took about 30 minutes. On the MBT-70, it required draining and refilling multiple hydraulic systems, checking computer diagnostics, calibrating sensors, and testing dozens of electronic subsystems. What should have been routine maintenance became a multi-day procedure requiring specialized facilities. The spare parts inventory was equally daunting. The MBT-70 contained over 50,000 individual components, many of which were custom manufactured and available from only one supplier. A single computer chip failure could disable the entire tank, and replacement parts often took months to obtain. The training requirements were becoming prohibitive. Tank crews traditionally learned their jobs in a few weeks of intensive training. MBT-70 crews needed months of classroom instruction, followed by extensive hands-on training with simulators and training vehicles. The learning curve was so steep that many experienced tank crews simply couldn't adapt to the new systems. By 1968, it was becoming clear that the MBT-70 had crossed a line from advanced technology into over-engineering. The tank was so complex that it was becoming operationally unfeasible. Each new system designed to solve a problem created two new problems, and the complexity was growing faster than the solutions. The first complete prototype was finally assembled in late 1968, and initial testing began in early 1969. The results were both impressive and terrifying. When everything worked correctly, the MBT-70 was indeed a marvel, fast, powerful, and incredibly capable. But everything rarely worked correctly for very long. System failures were constant and unpredictable. The suspension computer would crash, leaving the tank unable to adjust its stance. The fire control system would lose calibration, making accurate shooting impossible. The environmental system would fail, forcing the crew to operate with hatches open. The rotating compartment would jam, trapping the driver in whatever position he happened to be facing. Each failure required extensive diagnosis, specialized repair procedures, and often complete system replacement. The tank spent more time in the maintenance bay than in the field, and the maintenance costs were approaching the original purchase price of the entire vehicle. The engineering team was caught in a vicious cycle. Each attempt to fix a problem created new complications, and each new complication required additional systems and subsystems. The MBT-70 was becoming less like a tank and more like a research project that happened to have tracks and a gun. Of all the MBT-70's revolutionary features, none captured the public imagination or generated more problems than the rotating driver's compartment. This single design decision, born from a desire to solve a relatively minor operational issue, became the symbol of everything wrong with the project. The concept seemed logical enough. In traditional tanks, when the turret rotated to engage targets, the driver would lose his forward view and have to rely on periscopes, mirrors, or radio commands from the commander. This could be disorienting and dangerous, especially during high-speed maneuvers or in combat situations where split-second decisions meant the difference between life and death. The MBT-70's designers proposed an elegant solution. Mount the driver's position on a counter-rotating platform inside the turret. As the turret turned left, the driver's compartment would automatically rotate right, keeping him always facing the direction of travel. It was mechanically complex but theoretically sound. The engineering challenges were substantial. The rotating mechanism had to be smooth, silent, and reliable under combat conditions. It needed to maintain electrical connections for controls, communications, and displays while rotating continuously. The system required slip rings, rotary joints, hydraulic actuators, and a sophisticated control system to coordinate the rotation with turret movement. The first tests of the rotating compartment were conducted with the tank stationary, using experienced test drivers who were briefed on what to expect. Even under these controlled conditions, the results were disturbing. Drivers reported immediate disorientation, nausea, and difficulty maintaining spatial awareness. The problem was that human beings are not designed to rotate continuously while trying to control a moving vehicle. The inner ear, which controls balance and spatial orientation, becomes confused when the visual reference frame is constantly changing relative to the body's position. It's similar to the motion sickness experienced on ships, but worse because the rotation is active rather than passive. Dr. Sarah Mitchell, an aerospace medicine specialist who consulted on the project, described the effect. Imagine trying to drive a car while sitting on a slowly rotating bar stool. Your eyes tell you you're moving forward, but your inner ear tells you you're spinning. The brain can't reconcile these conflicting signals, and the result is severe disorientation and nausea. The first mobile tests were even worse. When the tank began moving while the turret was rotating, drivers experienced what test reports described as complete spatial disorientation. Several test drivers had to be helped from the tank after brief driving sessions, and some refused to continue testing. Sergeant First Class Robert Hayes, one of the primary test drivers, later recalled, "It was like being inside a blender while trying to drive a truck. You'd think you were going straight, but the tank would be turning. You'd try to turn left, but you'd actually turn right because you'd lost track of which way was which. It was terrifying." The psychological effects extended beyond simple motion sickness. Drivers reported anxiety, claustrophobia, and in some cases, panic attacks. The rotating compartment created a sense of being trapped in a mechanical nightmare, spinning helplessly while trying to control a 58-ton vehicle traveling at high speed. Engineers attempted various solutions to the human factor problems. They tried slower rotation speeds, but this defeated the purpose of keeping the driver oriented. They experimented with visual references and displays, but these only added to the confusion. They even tried medications to prevent motion sickness, but these impaired the driver's reaction times and judgment. The rotating compartment also created mechanical problems that hadn't been anticipated. The constant rotation put stress on electrical connections, hydraulic lines, and mechanical components. Slip rings wore out quickly, rotary joints developed leaks, and the control system required constant calibration and adjustment. Maintenance of the rotating system was a nightmare. Technicians had to work around rotating machinery, deal with complex electrical connections, and troubleshoot problems that only occurred when the system was in motion. Simple repairs that should have taken minutes stretched into hours or days. The reliability problems were compounded by the system's complexity. The rotating compartment required its own computer control system, hydraulic pumps, electrical generators, and backup systems. Each component was a potential failure point, and when any component failed, the entire system became inoperative. During one particularly embarrassing test in 1969, the rotating mechanism jammed while the turret was pointed 90 degrees to the left. The driver found himself facing sideways while trying to drive straight, with no way to correct his orientation. The tank had to be towed back to the maintenance facility, where technicians spent 3 days repairing the rotation system. The incident reports from MBT-70 testing read like a catalog of mechanical and human disasters. Drivers became sick and disoriented. Rotation mechanisms jammed or failed. Electrical systems shorted out due to the constant movement. Hydraulic systems leaked. Computer controls crashed. Perhaps most damaging was the realization that the rotating compartment solved a problem that didn't really exist. Experienced tank drivers had been successfully operating vehicles with rotating turrets for decades. The disorientation caused by turret rotation was minor compared to the complete spatial confusion caused by the rotating driver's compartment. The rotating compartment became a symbol of the MBT-70's fundamental problem: over-engineering. In trying to solve every conceivable operational issue, the designers had created solutions that were worse than the original problems. The tank was becoming too complex for human beings to operate effectively. Military observers from other countries watched the MBT-70 tests with a mixture of fascination and horror. The rotating compartment became legendary in defense circles as an example of how advanced technology could become a liability rather than an asset. Soviet intelligence reports on the MBT-70, declassified years later, revealed that Russian engineers were initially concerned about the tank's advanced features. But as details of the rotating compartment and other problems became known, Soviet attitudes shifted from concern to amusement. One report noted that the Americans appear to be defeating themselves with their own technology. The human factors problems with the rotating compartment highlighted a broader issue with the MBT-70 program: the disconnect between engineering capability and operational reality. Engineers could build incredibly sophisticated systems, but they couldn't always predict how human beings would interact with those systems under stress. By 1969, it was becoming clear that the rotating compartment was unfixable. The human factors problems were inherent to the concept, not the execution. No amount of engineering refinement could overcome the basic incompatibility between human physiology and continuous rotation while operating a vehicle. The rotating nightmare had become the MBT-70's most visible failure, but it was also symptomatic of the project's deeper problems. The tank had become so complex, so over-engineered, and so removed from operational reality that it was becoming unusable by the very people it was designed to serve. While the MBT-70's technical problems were mounting, an equally serious crisis was developing in the international partnership that had created the project. What had begun as a symbol of NATO unity and technological cooperation was becoming a diplomatic nightmare that threatened to destroy relationships between America's closest allies. The problem started with something as basic as units of measurement. American engineers worked in inches, feet, and pounds. German engineers worked in millimeters, meters, and kilograms. This might seem like a minor issue, but when you're trying to build precision machinery with tolerances measured in fractions of units, the difference between metric and imperial measurements becomes critical. Early in the project, both sides agreed to use metric measurements for all specifications and drawings. But American suppliers and manufacturers were deeply embedded in the imperial system, and converting everything to metric and added time, cost, and opportunities for error to every component and assembly. The measurement problem created a cascade of complications. American-made components didn't fit properly with German-made assemblies. Bolt holes were slightly off. Electrical connections didn't align. Hydraulic fittings leaked because of dimensional mismatches. What should have been simple assembly procedures became complex engineering challenges. But the measurement issue was just the tip of the iceberg. Deeper cultural and organizational differences were creating fundamental conflicts in how the project was managed and executed. American defense contractors were accustomed to cost-plus contracts, where the government paid for all development costs plus a guaranteed profit. German companies operated under fixed-price contracts with strict cost controls. These different business models created conflicting incentives. American contractors had little motivation to control costs, since overruns would be covered by the government. German contractors were highly motivated to control costs, since overruns came directly out of their profits. The result was constant tension over spending, schedules, and project priorities. the technical disagreements were even more serious. American engineers favored complex, high-tech solutions that pushed the boundaries of existing technology. German engineers preferred proven, reliable designs that could be manufactured efficiently and maintained in the field. These philosophical differences led to heated debates over every major design decision. The rotating driver's compartment became a particular source of international friction. American engineers saw it as an innovative solution to an operational problem. German engineers viewed it as an unnecessary complication that added cost and complexity without providing real benefits. The arguments over the rotating compartment consumed months of meetings and generated thousands of pages of technical documentation. Communication problems compounded the technical disagreements. Despite the use of English as the common language, subtle differences in technical terminology led to misunderstandings and errors. American engineers would specify one thing, German engineers would understand something slightly different, and the resulting components wouldn't work together properly. The project management structure was a diplomatic nightmare. Decisions required approval from both American and German authorities, but the approval processes were completely different. American decisions went through multiple layers of military and civilian oversight. German decisions involved different government agencies and industrial partners. Simple changes that should have taken days stretched into months of bureaucratic procedures. Quality control standards created another source of conflict. American military specifications were incredibly detailed and rigid, requiring extensive testing and documentation for every component. German industrial standards were equally rigorous but followed different procedures and criteria. Components that met German standards might not meet American standards, and vice versa. The testing protocols became a particular source of friction. American military testing was designed to evaluate performance under extreme conditions, often pushing equipment to the point of failure to understand its limits. German testing focused on reliability and durability under normal operating conditions. The different approaches led to different conclusions about the same components and systems. Security requirements added another layer of complexity to the international cooperation. Both countries had strict rules about sharing classified technology, but these rules weren't always compatible. Information that Americans considered routine might be classified by German standards and vice versa. The security restrictions slowed communication and made it difficult to share technical data efficiently. The financial arrangements became increasingly contentious as costs spiraled out of control. The original agreement called for shared costs and shared benefits, but as expenses mounted, both sides began questioning whether they were getting fair value from the partnership. Americans complained that German components were overpriced. Germans complained that American changes were driving up costs unnecessarily. By 1968, the international partnership was showing serious strain. Technical meetings became diplomatic negotiations. Engineering decisions became political issues. Simple problems required intervention from high-level government officials to resolve. The Colossal missile system became a particular source of international tension. The missile was an American development that the Germans were required to adopt for their version of the MBT-70. But the Colossal was experiencing its own development problems, with guidance failures, reliability issues, and cost overruns that rivaled those of the tank itself. German engineers wanted to develop their own missile system or adopt a proven European design. American officials insisted on the Colossal to maintain commonality between the two versions of the tank. The dispute consumed months of negotiations and delayed the entire project, while diplomats and engineers argued over technical specifications and political implications. What made the situation even more frustrating was that both sides were genuinely trying to cooperate and build the best possible tank. The conflicts weren't caused by bad faith or hidden agendas. They were the inevitable result of trying to merge two different technical cultures, business practices, and military traditions into a single project. The media attention made the situation worse. Defense journalists on both sides of the Atlantic began reporting on the conflicts and delays, often with incomplete information that exaggerated the problems and created political pressure for quick solutions. Politicians who had originally supported the project as a symbol of NATO unity began questioning whether international cooperation was worth the complications. The German government was particularly sensitive to criticism about cost overruns and technical problems. Germany was still rebuilding its military reputation after World War II, and the MBT-70 was seen as an important symbol of German technological capability. The project's problems were viewed as a national embarrassment that reflected poorly on German engineering and management. American officials were equally concerned about the political implications of the project's problems. The MBT-70 was supposed to demonstrate American technological leadership and the benefits of international cooperation. Instead, it was becoming an example of how good intentions and unlimited budgets could produce spectacular failures. By 1969, the international partnership was effectively broken, even though both sides continued to go through the motions of cooperation. Technical meetings became exercises in damage control. Joint decisions became unilateral actions that were grudgingly accepted by the other side. The spirit of collaboration that had launched the project had been replaced by mutual frustration and barely concealed hostility. The final blow came when the German government began quietly exploring alternatives to the MBT-70. German defense officials started discussions with other European partners about developing a new tank that would meet their needs without the complications of American cooperation. When news of these discussions leaked, it effectively ended any pretense that the MBT-70 partnership was still viable. By 1969, the MBT-70 had achieved a dubious distinction. It had become the most expensive military vehicle ever developed, with costs that defied all rational explanation. What had started as a $300 million program had exploded into a financial catastrophe that would ultimately consume over $1.5 billion, nearly $10 billion in today's money. The cost overruns weren't just large, they were unprecedented in their scale and scope. Each prototype tank cost approximately $25 million, making it more expensive than a squadron of fighter jets or a small naval vessel. For comparison, the Soviet T-62 tank, which the MBT-70 was designed to counter, cost roughly $100,000 per unit. The Americans and Germans were spending 250 times more money to build a tank that couldn't even complete basic field trials. The financial disaster began with the project's fundamental approach to cost estimation. In the early 1960s, defense contractors routinely underestimated costs to win contracts, knowing that overruns would be covered by the government. The MBT-70's initial budget was based on optimistic assumptions about technology development, manufacturing efficiency, and international cooperation, assumptions that proved to be completely unrealistic. The complexity of the tank's systems drove costs exponentially higher than anyone had anticipated. Each advanced feature required its own research and development program, specialized manufacturing equipment, and extensive testing procedures. The rotating driver's compartment alone consumed over $50 million in development costs, and it never worked properly. The hydropneumatic suspension system became another financial black hole. The original estimate for developing the suspension was $10 million. The actual cost exceeded $100 million, and the system still required constant maintenance and frequent replacement of expensive components. The Shalala missile system added another layer of financial disaster. Originally budgeted at $50 million for development and initial production, the missile program eventually consumed over $300 million and delivered a weapon that worked sporadically at best. The missiles themselves cost over $100,000 each, more than an entire conventional tank. Manufacturing costs were equally catastrophic. The MBT-70's advanced materials and precision manufacturing requirements meant that normal production methods couldn't be used. Specialized equipment had to be designed and built. New manufacturing processes had to be developed. Quality control procedures had to be invented from scratch. The armor system exemplified the manufacturing cost problems. Each armor panel required over 200 individual manufacturing steps, including specialized welding, heat treatment, and precision machining. The rejection rate for armor panels exceeded 50%, meaning that more than half of all panels produced had to be scrapped and remade. The electronic systems were even more expensive to manufacture. The tank's computers used custom-designed components that were available from only one or two suppliers. When components failed, which happened frequently, replacement parts often took months to obtain and cost thousands of dollars each. Testing costs spiraled out of control as problems mounted. Each test failure required extensive analysis, redesign, and retesting. The tank spent more time being repaired than being tested, and each repair cycle consumed hundreds of thousands of dollars in parts and labor. The international partnership, which was supposed to reduce costs through shared development and production, actually increased expenses significantly. Coordinating work between American and German contractors required extensive travel, communication, and administrative overhead. Technical disagreements led to duplicate development efforts and incompatible components that had to be redesigned. Change orders became a constant source of cost growth. As testing revealed problems with various systems, engineers would propose modifications and improvements. Each change required new analysis, new components, new testing, and new documentation. The cumulative effect of hundreds of small changes was enormous cost increases. The project's management structure contributed to the financial disaster. With multiple contractors, government agencies, and international partners involved, nobody had clear responsibility for controlling costs. Decisions that increased expenses could be made by any number of organizations, but there was no effective mechanism for preventing or controlling cost growth. Congressional oversight began to intensify as costs mounted. Senator William Proxmire, chairman of the Senate Banking Committee, began holding hearings on defense cost overruns, with the MBT-70 as his primary target. The hearings revealed shocking details about the project's financial management and technical problems. The most damaging revelation was that defense contractors had known about many of the technical problems years earlier, but had continued to accept funding without informing Congress or the Pentagon about the true scope of the difficulties. Internal company documents showed that engineers had identified fundamental flaws in the rotating compartment and other systems as early as 1967. The Pentagon's own cost analysis, released in 1969, painted a devastating picture of financial mismanagement. The report concluded that the MBT-70 program had no effective cost controls, no realistic schedules, and no clear performance objectives. It recommended immediate termination of the project. The German government was conducting its own financial review with equally disturbing results. German auditors found that their portion of the project had consumed over $400 million, nearly 10 times the original German budget allocation. The German Defense Ministry concluded that continuing the project would bankrupt their entire tank development program. What do you think about this level of financial mismanagement? Could better oversight have saved the project, or was it doomed from the start? Let me know your thoughts in the comments. The opportunity cost of the MBT-70 was staggering. The money spent on the failed project could have funded dozens of other military programs, built hundreds of conventional tanks, or developed entirely new weapon systems. Instead, it had been consumed by a single project that had produced nothing but expensive prototypes and bitter lessons. The financial disaster extended beyond the direct costs of the project. The MBT-70's failure damaged the credibility of defense contractors, reduced confidence in international cooperation, and led to much more stringent oversight of future defense programs. The indirect costs of lost trust and increased bureaucracy would continue for decades. The contractors involved in the project faced serious financial consequences. Several companies lost money on their MBT-70 contracts, despite the cost-plus structure. The technical problems and schedule delays consumed resources that could have been used on profitable projects. Some smaller contractors were nearly bankrupted by their involvement in the program. The political consequences were equally severe. Defense officials who had championed the project found their careers damaged by its failure. Politicians who had supported the program faced criticism from constituents and colleagues. The MBT-70 became a symbol of everything wrong with defense procurement and international cooperation. The final accounting of the MBT-70's costs was never fully completed. The project involved so many contractors, subcontractors, and government agencies that tracking all expenses was impossible. Conservative estimates put the total cost at over $1.5 billion, but some analysts believe the true cost was much higher when all indirect expenses are included. The financial disaster of the MBT-70 led to significant changes in defense procurement procedures. New regulations required more realistic cost estimates, better oversight of contractor performance, and clearer performance objectives for major programs. The reforms came too late to save the MBT-70, but they helped prevent similar disasters in future projects. The irony of the financial disaster was that the money spent on the MBT-70 was ultimately not wasted. It was invested in learning what not to do. The lessons learned from the project's failure directly influenced the development of the M1 Abrams tank, which became one of the most successful military vehicles ever built. But those lessons came at an enormous cost that shocked even the free-spending defense establishment of the Cold War era. On January 15, 1970, Secretary of Defense Melvin Laird walked into a Pentagon briefing room and delivered a death sentence. With a single announcement, he terminated the MBT-70 program, ending nearly a decade of development and over $1.5 billion in spending. The most ambitious tank project in history was officially dead. The announcement sent shockwaves through the defense industry and allied governments. Thousands of engineers, technicians, and support staff learned that their work on the tank of the future had been for nothing. Prototype vehicles that had cost $25 million each were destined for scrapyards or museums. The dream of technological superiority had become a nightmare of cost overruns and technical failures. But the story of the MBT-70 didn't end with its cancellation. In many ways, the project's most important chapter was just beginning. The failure of the MBT-70 would teach the defense industry lessons that would influence military vehicle development for the next 50 years. The immediate aftermath of the cancellation was chaos. Contractors had to shut down production lines, lay off workers, and dispose of specialized equipment that had been built specifically for the MBT-70. The German government, which had invested heavily in the project, faced difficult questions about their defense procurement procedures and international partnerships. The technical documentation from the MBT-70 program filled entire warehouses. Engineers had generated millions of pages of drawings, specifications, test reports, and analysis documents. Rather than simply discarding this information, the Pentagon decided to preserve it as a resource for future tank development programs. This decision proved to be one of the most valuable outcomes of the entire project. When work began on what would become the M1 Abrams tank in the mid-1970s, designers had access to the complete technical history of the MBT-70. They could see exactly what had worked, what had failed, and why. The Abrams development team approached their task with a philosophy that was the exact opposite of the MBT-70's approach. Instead of trying to incorporate every possible advanced feature, they focused on proven technologies that could be manufactured reliably and maintained in the field. Instead of pursuing revolutionary innovations, they sought evolutionary improvements to existing systems. The contrast between the two projects was stark. Where the MBT-70 had a rotating driver's compartment, the Abrams had a simple, fixed driver's position. Where the MBT-70 had a complex gun launcher system, the Abrams had a conventional but highly effective cannon. Where the MBT-70 had exotic materials and manufacturing processes, the Abrams used advanced but proven technologies. The Abrams did incorporate some technologies that had been developed for the MBT-70, but only after they had been simplified and proven reliable. The advanced fire control system, the turbine engine, and the composite armor all trace their lineage back to MBT-70 research, but in forms that were practical and maintainable. The success of the M1 Abrams vindicated the lessons learned from the MBT-70's failure. The Abrams became one of the most successful tank designs in history, serving effectively in multiple conflicts and remaining in production for over 4 decades. Its reliability, maintainability, and combat effectiveness proved that advanced technology didn't have to be complex or exotic to be superior. The international partnership aspects of the MBT-70 also provided valuable lessons. The difficulties of coordinating development between different countries, technical cultures, and business practices led to new approaches for international cooperation. Future joint programs would have clearer management structures, better communication protocols, and more realistic expectations about the challenges of international collaboration. The financial disaster of the MBT-70 led to fundamental changes in defense procurement procedures. The Pentagon implemented new cost control measures, more rigorous technical reviews, and stricter oversight of contractor performance. The era of unlimited budgets and optimistic schedules was over, replaced by more disciplined approaches to program management. Congress also learned important lessons from the MBT-70 debacle. The hearings conducted by Senator Proxmire and others revealed the need for better legislative oversight of defense programs. New procedures were established for reviewing major programs, and Congress became much more skeptical of contractor claims about costs and schedules. The human factors lessons from the MBT-70 were equally important. The rotating compartment disaster highlighted the need to consider how human beings would actually interact with advanced technology under stress. Future military vehicle designs would include extensive human factors and testing and evaluation from the earliest stages of development. The MBT-70's legacy extended beyond tank development to influence the entire defense industry. The project became a case study in engineering schools, business schools, and military academies. Students learned about the dangers of over-engineering, the importance of realistic cost estimation, and the challenges of managing complex technical programs. Some of the engineers who worked on the MBT-70 went on to have distinguished careers in other programs, bringing with them hard-won wisdom about what worked and what didn't. Their experience with the project's failures made them valuable contributors to more successful programs like the Abrams, the Bradley fighting vehicle, and numerous other military systems. The German experience with the MBT-70 led to their development of the Leopard 2 tank, which incorporated many lessons learned from the failed joint program. The Leopard 2 became one of the most successful European tank designs, proving that the Germans had learned from their MBT-70 experience and applied those lessons effectively. The Soviet Union, which had watched the MBT-70 program with great interest, drew their own lessons from its failure. Soviet tank designers concluded that complexity was a weakness rather than a strength, and they focused on developing simple, reliable designs that could be manufactured in large quantities. This philosophy served them well in their own tank development programs. The MBT-70's influence can be seen in modern military vehicle development, where the lessons of over-engineering and complexity are still remembered. Today's military vehicles are certainly advanced, but they're designed with careful attention to reliability, maintainability, and human factors, lessons that were learned the hard way from the MBT-70's failure. The project also influenced civilian technology development. Many of the advanced systems developed for the MBT-70, computer controls, hydraulic systems, advanced materials, eventually found applications in civilian vehicles and equipment. The technology wasn't wasted. It was simply applied in more practical and cost-effective ways. What's your take on this? Do you think the MBT-70's failure was ultimately beneficial for military technology development? Could the same lessons have been learned without such an expensive disaster? Share your thoughts in the comments below. The MBT-70 prototypes that survived the program's cancellation became museum pieces and training aids. Today, visitors to military museums can see these mechanical marvels and wonder at the ambition and complexity that went into their creation. They serve as tangible reminders of what happens when engineering capability exceeds practical wisdom. The project's documentation continues to be studied by researchers and historians interested in the intersection of technology, politics, and military affairs. The MBT-70 represents a unique moment in history when unlimited resources were applied to an unlimited problem with predictably unlimited complications. Perhaps the most important legacy of the MBT-70 is the recognition that failure can be as valuable as success if the lessons are learned and applied properly. The project's spectacular collapse provided insights that couldn't have been gained any other way, and those insights influenced decades of subsequent development. The MBT-70 stands as a monument to human ambition and ingenuity, but also to the dangers of unchecked complexity and unlimited budgets. It reminds us that the most advanced technology isn't always the best technology, and that sometimes the greatest innovations come from learning what not to do. In the end, the MBT-70 achieved a kind of immortality through its failure. While successful tanks are eventually replaced by newer designs, the MBT-70 remains frozen in time as the ultimate example of what happens when engineering ambition exceeds practical wisdom. Its legacy continues to influence military vehicle development, serving as both inspiration and warning for future generations of engineers and designers. The story of the MBT-70 is ultimately a human story, a tale of brilliant engineers who pushed too hard, ambitious politicians who promised too much, and practical soldiers who had to deal with the consequences. It's a reminder that behind every great technological failure are real people who believed they were building the future, even when that future proved to be impossible to achieve. That's the story of the MBT-70, the atomic supertank that collapsed under its own complexity. From its ambitious beginnings in the Cold War era to its spectacular failure and lasting legacy, the MBT-70 represents both the best and worst of human technological ambition. What did you think of this deep dive into one of history's greatest engineering failures? Do you believe the lessons learned were worth the enormous cost, or could those insights have been gained through less expensive means? I'd love to hear your thoughts in the comments below. If you enjoyed this exploration of unrealized technologies and monumental failures, make sure to subscribe to Never Built for more stories of the technologies that never were. Until next time, remember that sometimes the greatest lessons come from the most spectacular failures.